Hello, I'm Yaroslav Melekhov, and I'm going to present our work DGC-Net, Dense Geometric Correspondence Network. This work addresses the challenge of dense pixel correspondence estimation between two images. We are given a source and a target image, and we predict a dense pixel correspondence map F in such a way that the source image is aligned to the target one. The proposed approach is based on classical image alignment pipeline and consists of three main steps. More specifically, feature extraction, matching, and coarse to fine correspondence map estimation. The spatial resolution of the output correspondence map F is equal to the size of the image pair, establishing pixel-to-pixel correspondences between two views. Each block of the pipeline is implemented using differential operations, such that the whole pipeline is trained end-to-end. Since it is very challenging to estimate correct correspondences for ill-posed cases, such as occluded regions of an image pair, we complement the original structure by a mask decoder, which predicts a measure of confidence, a binary mask, of each correspondence. Feature extraction part, correlation layer, correspondence map and mask decoders are organized as CNN structure called DGC+M-Net. Let's take a look at each of these steps in more detail. The first step is feature extraction. Usually, as it is shown in optical flow methods, in order to cope with large motion, one can create an image pyramid and estimate the motion layer by layer iteratively. Since the motion is much smaller for the small image size on the top of the pyramid, it is easier to estimate motion vectors. Utilizing similar idea in the case of strong geometric transformations, we construct a hierarchical representation of the input image pair in feature space. To do that, we use a Siamese neural network with two branches with shared weights. The branches use the WGJ16 architecture trained on ImageNet and truncated at the last pooling layer. The weights of this part have been frozen during the training. The next step of the pipeline is matching. In order to estimate the similarity score between two images, we calculate the correlation volume between the normalized feature maps of the source and target images. More specifically, we compute global correlation and apply L2 normalization before and after the correlation layer to strongly downweight ambiguous matches. It's important to note that the third dimension of the cost volume is a product of its width and height. Thus, it is not feasible to calculate such volumes in the bottom layers of the pyramid, where the spatial resolution of the feature maps is large. Therefore, at the bottom feature pyramid layers, we concatenate descriptors channel-wise. The next step is cost to fine correspondence map estimation. Once we create a feature pyramid of the source and target images and calculate the cost volume, we then feed this volume into a fully convolutional correspondence map decoder, which predicts a 2D correspondence field with the same size as the input features. We upsample the predicted map F by using bilinear interpolation and warp the features of the source image at the next level of the feature pyramid. Finally, the upsampled map, warped source and target features are concatenated along the channel dimension and provided accordingly as input to the decoder at the next level. Furthermore, iteratively applying these operations, we can refine the estimate from the top to the bottom level of the feature pyramid. We train our model on synthetic transformations applied to Pascal VOC11 and Tokyo Time Machine dataset. To check the image alignment performance of the proposed approach, we evaluate the model on H-patches dataset, consisting of several sequences of real images, with varying photometric and geometric changes. In addition, we apply our method to the problem of relative camera pose estimation. For this purpose, the DTU dataset has been used. Qualitative results are presented in this slide. As you can see, our method can cope with large geometric transformations, such as rotation and translation, between two images, leading to better image alignment. In addition to image alignment, we demonstrate the application of the proposed method for predicting relative camera pose, and report median orientation and translation error. The proposed approach outperforms all CNN-based methods. Interestingly, DGC+M-Net falls slightly behind of DGC-Net in estimating relative pose. However, it achieves significant advantages in terms of computational efficiency, thanks to the predicted binary mask. Thank you for your attention, and I hope to see you at the poster.